And let's move to the next presente outcome.
My project for this summer, I was working on classical linear elasticity and bond-based pair-dynamic models with my mentor, Patrick Delhite, and he also has a partner on his research project, Serge Prudhomme, who helped us a lot this summer with my project. All right, so a quick overview. We're going to talk about what is bond-based pair dynamics, a little bit of my REU goal, and some different coupling methods that we use, and some coupling data that we'll go over. So a few definitions. We have pair dynamics, which is our non-local model here, a form of mechanics, which is just concerned with some discontinuities and fractures. Then we have linear elasticity, our local model, a mathematical model of how solid objects deform and become internally stressed due to different loading conditions, which we will see later. And then we have coupling approaches, which is where we couple those local and non-local models, and we pair them to combine the efficiency of the local models and the accuracy of those non-local models. And then we have modeling error, which we will see later on some plots, which is the difference between the solution to the coupling approach and the solution to the classical linear elasticity model. All right, so here is a graph which just shows linear elasticity versus a pair dynamic model. So this summer we used this model where we were holding two rubber bands, we were holding them both on both ends. And a force was applied to the top where somebody pulled the rubber band. So in the linear elasticity model, this is without coupling. It goes on linearly, it would go on infinitely in that, straight infinitely in that area. But in our pair dynamic model, it would travel linearly, similar to the linear elasticity model, but at some point, because of the force, it would fail, which we see here. It's just model that 2 is where it fails. So we wanted to use coupling so we can combine the method of the linear elasticity model, which is going on infinitely, and this pair dynamic model, so we can get a better method. So we used lots of different coupling approaches. Oops. So my goal for the summer was to investigate the coupling of the local and non-local models to combine the benefits of both. All right, so there are 3 different types of coupling methods. We have coupling where we match the displacements between the models. We have coupling where we match the stresses, and then coupling with a variable horizon. This summer, what you'll see is just data based on coupling with matching displacements, which is what I have worked on for the entire summer. So right here we have a model which showcases our linear elasticity model, which is in the black filled in dots, and then our pair dynamic model, which is in the open white dots. So what I said before, coupling where we match our displacements, right here in the overlap region where the pair dynamic has overlapped into the linear elasticity area, we match our displacements, this point and this, they're both matching, these are both matching. And what I was doing, I was going in, this point does not have a matching displacement, so we would do an interpolation. I did linear interpolation, I also did quadratic interpolation. So that's what we were doing. And we were also experimenting with the nodal spacing. So right here, we have a nodal spacing of 1/8 in our linear elasticity region, and nodal spacing of 1/16 in our pair dynamic region. And this is also the linear elasticity region of 1/8. But we also have different diagrams where we had a nodal spacing of maybe 1/16 here. We also had a region of maybe 1/32 here. So we just did a lot of experimenting with different regions and also different methods for interpolation, whether that be linear or quadratic. So now we're about to see a few different plots. So here on the left, we have our linear interpolation, and this is with a quadratic loading condition. So in our linear interpolation, we have the blue plot, which is at 1/4 for our coupling. We have 1/8 for our coupling here at the orange. And then at the green, we have 1/16. And then this red plot is a plot where there is no coupling. It's just the, it's just the linear elasticity region, and there's no coupling, which we talked about earlier, where we will see modeling error, which is where we compare this red plot with the rest. And on this side, we have the quadratic interpolation. We see that when we do it quadratically, the error is a lot less. You see our plots our lines are way more close to the red line. It's a lot more accurate when we do our quadratic interpolation. Okay, and here are our error plots. So we see here in the linear elasticity error plot, we have an error. It's really great right here for our 1/4. And then at 1/8, our error gets smaller, which we would assume. And as we get smaller and smaller with our nodal spacing, the error also gets smaller and smaller. And then here in our quadratic interpolation, we see that the error is already a lot smaller, even when we have our nodal spacing of just 1/4. But as we get all the way to 1/16, comparing the error right here, this is 0.02, here our error 0.05. So we can compare and contrast those errors when we do a linear interpolation versus our quadratic interpolation. And we also have cubic solutions. So here is the exact same method and formula that we used earlier, but instead of having a quadratic solution, we have a cubic solution. We see the same plots here in red, which is the non-coupled plot. And then in our different colors, we have the nodal spacing again of 1/4, 1/8, and 1/16. And we can see what it looks like in our linear interpolation versus what it looks like in our quadratic interpolation. And as we predicted, the quadratic interpolation is more efficient, it works better. And then in our error for the cubic linear interpolation, we see again how the error of 1/4 is extremely great compared to our error of just 1/16, where we have smaller amount of error. Also in our quadratic interpolation, our error at 1/16 is even smaller than it is in our linear interpolation. We also did different plots for a different boundary condition. This is called the Newman boundary condition. Originally, I said we were holding a rubber band fixed on both sides, but in our Newman boundary condition, we have our rubber band fixed on one side, fixed only on one side, where we can see that it's only fixed at one point, on the other point it is not fixed. So that's the difference between our Newman boundary condition and the original one, which we showed earlier, where we were fixed on both sides. So again, it's the same plots, the plots at 1/4, 1/8, and 1/16. And we can see that our error, the quadratic right here, you can't really see it. It's really hard to see the different ones because it's so close in together, which we predicted. It's a lot more efficient than our linear interpolation on this side. And then again, we have the error plots. And we can see that on our linear side, our error is a lot greater than it is when we did our quadratic interpolation. All right, and those are some of the references that I had, and that's all that I had for today. Any questions?
Yeah, I have a couple of questions. I mean, when you say the cubic, when you show the cubic plot, the displacement is the displacement. I mean, are you plotting the position of the different pieces of the rubber band, or?
No, so we're plotting the cubic plot. It's not the positions of the rubber band. The rubber band is just like we didn't actually have a rubber band. That was just the scenario that we're using. What we're plotting here is we have different forces that we use. So on a cubic solution, we had different formulas that we would input into our code, which is why it's in the cubic shape rather than the quadratic one.
But
So
you label as displacement. The vertical axis you label as displacement. Normally, displacement is how much a piece of the material have moved from the equilibrium position. I mean, I don't know.
Yeah. No, it's correct. It's the displacement.
So this is a rubber band that is in that shape, in a cubic shape, or?
No, it's the displacement.
Okay. So this is a rubber band that is in that shape, in a cubic shape, or?
Yeah, you have a rubber band, which is in a straight line, and then you apply the force, and then you get this cubic shape. Because you're pulling, that the force results in this cubic shape.
Okay, so you are pulling from 2 points in opposite directions. Okay.
Yeah.
Okay. Yeah, and my second question, when you compare the linear interpolation with the quadratic interpolation, the errors of those two methods, it looked that the error in the quadratic is around half of the error in the linear. For more, I mean, yes, it looked like that in most of your plot. So if that's the case, I mean, are you gaining, I mean, how, because to do the quadratic interpolation will cost you more operations. So could you, I mean, are you getting the same result that just using a finite mesh, but with the linear interpolation? Could you reduce the error by half just in that way? You know, be equally efficient? I don't know if you have thought about that.
I'm not sure if I understand your question, but if you're asking the methods that we used, could we just use the linear interpolation and get the same data as when we use the quadratic interpolation?
Yeah, the quadratic error, it looked like it's half of the other error, not for most of your plot. But to do the quadratic interpolation is costing you more operations. The computer have to do more operations. So if you use that additional computing time for doing a finer mesh and using the linear interpolation, I mean, you know, eventually you want to find out what is more efficient, the quadratic, you know, or the linear, you know. So I'm just curious if you have thought about doing that experiment.
Now, I personally have not, but I still will be working on this project. So that's something that we could take into consideration going in the future.
Okay, thank you.